All right, let's look at some of the stuff from 5.3. So I'm going to go through both of these exercises. The other exercises in the book, the examples in the book are quite good. But I think, maybe I can go through these two exercises here. I'll go through them in order. I'll do the first one that's at the top first. I will make a note on this one right here. This is not quite right. This should actually say 5 divides. We'll say n to the 5th plus 4n minus 10. Right, and we'll do that when we actually do it down here. Right. So, right, induction is what we're going to use. Right, so I want to prove that for all integers n, 5 divides that expression right there, n to the 5th plus 4n minus 10. Right. So what's the first thing? Right, induction is always a two-part process. Step 1, I always do my basis step. Right, I guess I could say proof. Right, we could say by induction. Right, so what's the basis? Well, since it looks like it's all integers, right, the basis I want to show, right, and I use a slightly different notation from the book, right, but I want to show that p of 0 is true. Right. Now, what does this mean? It means that I want to show that when n is 0, right, because that's sort of what this thing is in here, right, we want to show that the statement is true. Well, when n is 0, right, so to do this, just let n equal 0. Right, then I get 0 to the 5th plus 4 times 0 minus 10, right, and clearly 5 divides negative 10, right? Just think of it, right? What number do I multiply 5 by to get the negative 10, right? So I could write negative 10 as 5 times negative 2. So, in fact, I can find an integer, right? So, now, right? That means p of 0 is true, right? Now what's the next thing, right? Next is the inductive step. Right? Remember this, I'm going to assume, right, p of k is true, and that is I'm going to deduce p of k plus 1. Right? So in this case, what does it mean? Well, I want to show, right, by supposing that 5 divides k to the 5th plus 4k minus 10, that I can deduce that 5 divides k plus 1 to the power 5 plus 4 times k plus 1 minus 10. Right. So, right, what are we going to do? We're going to suppose that suppose p of k is true. Right, that is, that is that 5 divides k to the power 5 plus 4 times k, minus 10. I wrote a little weird thing right there. Maybe I can I erase that? There we go. Okay. Now, what kind of nice thing I could do here is just say consider the quantity Right? Notice this is the thing I want to show is divisible by 5, right? And, well, you'll see what happens here, right? I'm going to expand all of these out, right? And then see what I'm left with. So if I expand this first thing out, I get k to the 5th plus, let's say 5k to the 4th, plus, this is going to give me 10k third, plus, my goodness, 10k squared plus 5k plus 1, right? So this is all this thing here, right? I'm going to continue on in the next line here. So then I'm going to multiply through here, plus I've got 4k plus 4 minus 10. Now this looks like a bunch of stuff here, but something really nice is going to happen. Notice I have this thing here, I have this thing here, and I have this thing here, right? If I group these together, what do I know from my inductive hypothesis? Well, I know that if I bring these out here, that k to the 5th plus 4k minus 10, right? If I sort of keep those by themselves and then get the rest of this junk over here, I'll group it all, the rest of the stuff here. 5k to the 4th plus 10k 3 plus 10k 2k plus, really, plus 5. Well, I know by the inductive hypothesis that this is actually divisible by 5, right? I know that this is just 5 times something, right? I could say m, right? But notice also this whole thing over here. This 5 is a multiple of 5. This is a multiple of 5. 5, 5, 5. So what can I do? I can pull a 5 out of everything, right? So I forgot my equal sign over here, right? So notice that this is equal to 5m plus, right? I can pull a 5 out, and I've got 5, right? K to the 4th plus 2k cubed, right? Plus 2k squared plus k plus 1. And then, right, once again, I can pull a 5 out, right? And this gives me that this is just 5 times m plus, right, all of this stuff. Now, what do I know? I know that m is an integer, right? Because by our inductive hypothesis, this was divisible by 5. So I know that there's an integer m, right, that can go there. And that k, all of these k values here, well, these are just natural numbers, right? So this is the numbers 0, 1, 2, 3, all the way up. So that's kind of nice, right? So those are also integer numbers, right? Because they're the natural numbers are a subset of the integers. So I can certainly find an integer here. So this is just 5 times something, right? We can call it r. Therefore, right, 5 divides k plus 1, the 5th, plus 4, right? Which is what we wanted to show. So there we we go. There it is. Right. So that's not so bad. Now let's do this last one. This actually is a lemma. So what was happening in this one is this actually came from something else. You're trying to prove that you're trying to prove something about 2 to the k and k squared, I believe. Yeah. You're trying to prove that 2 to the k, 2 to the k is greater than or equal to k squared, something like that, maybe, for some value of k. Something like that, right? And you get into this problem where you have your you're multiplying some values or adding some values on either side in order to get it into the form that you actually want. And what comes up is it becomes necessary to actually prove this lemma up here, and actually to make sure you sort of, it's basically like, if this thing holds, then the rest of the stuff is true. So, you know, this is sort of a detail we're going to go back and fill in this exercise. So we want to show that for n greater than or equal to 4, 2n plus 1 is less than or equal to n squared, right? So in this case, we want to show my basis, right? So proof So in the basis step, I can always show what's going to happen first. Now, in this case, they're actually quantifying it over all integers, or all, all natural numbers. But then they sort of have this other conditional statement. If it's greater than 4, then this is the case. What I'm actually going to just do is say for all n greater than 4. And that way I don't have to really worry about that, right? So that's sort of, this is sort of an addendum, right? I guess I should probably do it beforehand, but I'm just stating it now. So really my basis is showing that P of 4 is true. Right? So when n is 4, what do I get? Well, I get 2 times 4 plus 1, right? This is my sort of left-hand side, right? Well, what is that equal to? That's equal to 8 plus 1, that's equal to 9. And then on the right-hand side, I've got 4 to the power of 2, which is 16, right? Right, and it's true. It's true that 9 is less than or equal to 16, right? So the basis step is true. It's true when n is 4. So now what do I need to do? Well, I need to show that if I suppose P of k, if I suppose that that P of k is true, I need to be able to get to P of k plus 1 being true, right? Now, so now I have the inductive step. Suppose suppose P of k is true. Well, then it's true that 2 k plus 1 is less than or equal to k squared. So one thing I can actually do is that if I add numbers to each side, right, that'll actually allow me to keep this inequality as long as it's as long as the numbers are less than or equal to one another. Right? So let me just add 2 over here, and then add 2k plus 1 over here. Right? So one thing I could actually think about is that, well, it's certainly true that 2k plus 1 is greater than 2, right, when it's 4. And since 2 is just a fixed number, if I keep increasing k, right, it'll be always true, right? So if I'm adding a larger number on the right and a smaller number on the left, right, then this inequality will still be true, right? Because if you think about it, if I added equal values on the left and the right, the inequality would be true. If I had a smaller value on the left and a larger value on the right, then obviously the inequality will still be true as well. So what does this give me? It's actually going to give me something quite nice. I chose these on purpose, and this is sort of a time when, you know, maybe you've sort of figured out some things about writing proofs. Like sometimes when we write proofs, they're kind of like they're kind of like these puzzles we have to solve, and sometimes we have to be a little bit clever when we're solving the puzzle, right? And so the reason I chose these is because I worked out, well, what I actually need to do. And you'll see why I chose these. So notice here I've got, and I'm actually not going to add all these together just yet. So I've got 2k, right, plus 2 plus 1 less than or equal to, right, k squared plus 2k plus 1. Right. So what do I have on the left side? Well, I can actually factor this out here. And I'm left with 2 what do I have on the left side, or on the right side? Well, k squared plus 2k plus 1, that looks a lot like this. And isn't this actually what I wanted to show, right? So, right, that lemma holds. That means that very original proof, right, the last proof that they showed actually holds as well. All right, thanks.